Okay, so hi everyone. Yeah, as just introduced, so this is a presentation for Axial Generation, so a concretism-inspired method for synthesizing highly varied artworks. And the paper is written by Aniko, Ekart, Ulysses, Bernardet, and myself. And what we can see here is just a short video of some of the 3D output just animated together from the Axial Generation process. Okay, so when we're considering making or generating artwork, especially in an evolutionary context, there's three main aspects that we need to consider. So the first one's the internal representation of our artwork, or the genotype, and how we can represent things that are suitable to be crossed over and mutated, and all of these other processes. We also have to consider the assessment of our artwork. And then finally, we also need to consider how we generate or render our artwork from our selected genotype. So any choices that we make for any of these three aspects introduces kind of different constraints onto our system. And these can, will affect the visual characteristics of the final output, including things like the patterns that are present and the kind of color and other kind of visual characteristics. And the process we're introducing today is a new process which generates a wide range of visually varied and interesting artwork. And it will be used moving forward to help identify and hopefully formalize aspects of aesthetic judgment of 3D artwork. Okay, so we have a wide range, as everyone here will know, a wide range of existing systems which generate various sort of contents, either both 2D and 3D, that are being used. And as part of this, we also have a wide range of genotypes that are being used. So we use expressions, including their encoding in trees, CPPNs, shape grammars, and custom representations. And these have been used to great effect to generate a range of output, including sculptures, images, architectural designs, and as we just saw, dance as well. So the question might be raised is why would we need a new method to be generated or to be created? And the project that's currently being run, it was kind of, the idea was that the existing systems were not entirely appropriate. So one thing that was deemed important as part of the project was the ability to be able to create 3D items and then be able to compare them to 2D representations. And this is introduced into the process here today. Also, we wanted to avoid the use of kind of 3D specific genotypes, such as shape grammars based on 3D items, as this potentially reduces our ability to generate both 2D specific and 3D items, and also will potentially introduce additional constraints onto our system, which is something we want to try and avoid as much as possible. And also, the process is based on expression trees to help us with the kind of versatility and the applicability of this process to new and existing systems. The final consideration, which was deemed to be very, very important, was the performance requirements. So a lot of existing systems which work with expression trees work directly with the pixels or the voxels of a 2D or 3D item, and these can make this basically makes performance very, very high requirements and makes them less suitable for environments such as virtual, augmented reality, or online systems. And one thing that we wanted to try and achieve was the ability to be able to create these large-scale sculptures and high-resolution images within this process as well. Okay, so as we talked about a couple of slides ago, assessing the generated output is often delegated to a human user who uses their own intuition to judge the artwork which is generated. However, there's a few problems that can occur as a result of this. The user can often become bored and frustrated. And this is often one of the reasons that's often cited for this, is that the output that's generated is not complex or interesting enough to engage the user. So one reason we can think about this is, especially if we use expressions as our genotype, is expressions are very, very minimally constrained. They can potentially kind of create any color or any visual value for any pixel or voxel in the image or sculpture. And this makes our search space incredibly or very huge and very, very wide, and makes it very difficult to locate these kind of interesting and complex images. And so in order to fix that, what we can do is add additional constraints onto our search space to help try and improve this process. So ideally, what we would do is just constrain the search space to only include items that the user already finds aesthetically pleasing or interesting or wants to see. However, it's virtually impossible to be able to fully describe aesthetic preference. So what we do with the axial generation process, or AGP, is constrain or add constraints onto a system by applying the concrete art style. And this includes constraints, so placing items within a limited 3D space, limiting the number of items that are present within the output, and also using simple geometric shapes to form the patterns. Okay, so I'm sure many of you will know about concrete art, but for those who don't, so concrete art is just basically a subset of abstract art that's entirely free of any basis in observed reality and has no symbolic meaning. Yes, it has several well-defined tenets that describe what makes a concrete art, what artwork is included within this term. And this includes things like using an exact technique. The elements that make up the artwork are very simple, and also that the concept must be complete in the artist's mind before rendering. And I think this is the equivalent in our system of encoding the image with the explicit kind of expression trees before we then render afterwards. So why this makes a good choice for evolutionary art systems is that it allows us to ignore any unintentional representational aspects that we may generate. The well-defined tenets can be easily applied to our systems, and also the term is applicable to both 2D and 3D artwork. Okay, so the AGP works by maintaining 3 expression trees, and these were used to calculate the height, angle, and radius of the various points we place in 3D space. And what we can see is the image on the bottom right is how we use each of these values. So the height is the distance from the base of the artwork. The radius is the distance from a central axis, and the angle represents the angle around the radius. In addition to this, we also the process also exposes 8 parameters to give us kind of more control over what the style and type of items that we create. And this includes things like the total number of items we will place, the maximum height and radius, and then also rendering specific options as well. So this will include things like the size of the elements and the height and the width of the canvas that we use. And these can be used really to help us get a wider range of elements or items generated as output. Okay, so the rendering of the 3D items is a relatively simple process. All we need to do is place a specified geometric shape at the specified point in 3D space. And this can be done very simply using any kind of 3D graphics engine. So online systems, we can use 3JS, or you can use Blender or Unity as well. And the examples we can see at the bottom here were rendered within the Unity engine. Rendering the 2D items is a slightly more complex process. However, it was designed to mimic the process of creating 2D representational art, where what we do is we take the 3D item and abstract it down onto a 2D plane. And the examples we can see at the bottom of the slide here represent the top-down view of the 3D structure that we created using the process. So one thing you may notice as well, especially with the image, the third image from the left, is that each of the items that are placed can have differing sizes. And this is introduced through a concept of perspective that we add into the process. So items that are close to the top of the item are larger, and items close to the bottom will be smaller. And this can be turned on and off depending on the parameters that you send into the process. Okay, so aside from meeting the requirements that we outlined at the beginning of the presentation, the AGP also needs to be able to produce artifacts of interest. And one way we can think about artifacts of interest is in terms of their novelty and their value. So the novelty and value are very context-specific measurements. And so instead of looking directly at the value and novelty, we can kind of assess the system for its versatility or the potential of the system to create a wide range of items which showcase kind of a variety of aspects, including kind of a variety of values for aesthetic measures. So in order for us to assess the AGP, we performed a small run using 3 different measures. So the first one was symmetry, and we used a 3D detection algorithm for symmetry. The complexity, which basically measured the approximate visible vertices in the final output. And then finally, the compressibility using the normalized Kolmogorov complexity using zip compression. In order to do this, we created 500 items in both 2D and 3D, and they were randomly generated using this process. And then we calculated the value for all of the measures for all of these items, and we can see the results here. So we've got the 3D items on the left 2 graphs and 2D on the right 2. And the one thing that's quite obvious, or can be quite obvious, is that we've got these very large gaps on some of them. So the more obvious ones on for the compressibility, here we have these large gaps on the left-hand side where we didn't generate any items which had a value lower than 0.6. And we also saw this with the symmetry and complexity, albeit slightly less obvious regions where we don't have any items with kind of a high level of symmetry and complexity, and for 2D, kind of this mid-range of symmetry and high level of complexity. But one of the things that was obvious, especially for the symmetry and complexity, is that we did cover the entire range of the symmetry and complexity values. And this is partially what we were looking for when we're trying to assess the kind of versatilities. We had this kind of very wide sort of distribution across all values that were available. Okay, but as we just saw, there were some very notable gaps that were present in the values. So one thing that was important to try and determine is whether this was caused by the process and whether it's caused by the constraints we were adding onto the system, or some other reason that was preventing these items from being generated. And in an attempt to fill these, we ran several small evolutionary algorithms to try and fill these gaps. So we maximize the symmetry and complexity, and then additionally minimize the compressibility for both the 2D and 3D items. And what we can see is the evolutionary parameters at the bottom of the slide. And one thing you can notice is we only performed a small number of generations for each of these runs. Really is this just trying to get an indication of what the cause of the issue may be. And as we can see here, these are the results of the items after the evolutionary processes have been run. And what we can see is we didn't really fill these gaps. So especially with the compressibility values, we still had these very large gaps of values on the left-hand side and less than 0.6. But we also still saw it with the symmetry and complexity values, where we still struggled to kind of maximize both of these values together. I guess we believe that this, or one of the major causes of this is due to the measures that were being used, and they played kind of a very large part in these gaps being present. So for the symmetry and complexity, this is relatively intuitive, and we shouldn't necessarily expect values for high complexity and symmetry, as they are trying to measure the opposite attributes in these items. So something with a high level of symmetry will be more ordered and therefore potentially measured to be as less complex. And this really highlights the discrepancy between the measures that we may use to kind of evaluate these items, and also our kind of internal perception, where we would quite happily be able to think of something that would be both symmetrical and complex. For the compressibility measure, I think this was due to the implementation, so encoding all of the items into JSON and then encoding that into zip compression may have given us kind of a very limited redundancy, which would have led us to have a, or kind of mean that higher values were found on this process. And so that may be something, again, just the kind of encoding may have been the problem there with trying to get a wide range across the compressibility measure. Okay, so we talked about the novelty and the value being context dependent. And so to highlight this, the slide background that we've been working today was generated using the AGP. And we think this has kind of a very high value in this context. So there's space in the middle to put information. The pattern is there to help keep interest, but it's not overly complex to order to distract from the presentation. However, they wouldn't potentially be particularly well valued as a piece of art. It might be too simplistic and not interesting enough. And what we can see here is just the expression trees that we use to calculate all the values, the parameters that were provided to the process, and also the measure values were calculated for this image. And then another aspect which this highlights is also the performance ability or performance of the process, where we can see that we can quite easily create high resolution items. So almost a 4K resolution for these images. And the total number of calculations is the 200 items that we place, rather than working directly with the pixels and voxels, which would be roughly 8 million or so items. And so we can very quickly create these kind of very high resolution images. So in conclusion, the AGP meets the requirements that we talked about at the beginning. So we can generate 2D and 3D content. And we basically managed to do this by explicitly constraining the process using the concrete art style. And as we saw with the previous slides, the performance was suitable, which makes the process suitable for kind of implementation within a virtual reality system or online system, which is how it will be used moving forward within the project. We also think that it shows a high level of versatility as well. So it's capable of generating visually varied and interesting items. And it does this in a few ways. So there's multiple ways that the output that is generated can be explored. So we can either do this by evolving or changing the parameters, as well as the expression trees, which are used to calculate the positions. And we also saw that we had a range of values generated from items across multiple measures, so the symmetry and complexity especially. But what we also saw with this is the need for a process, or the process of all the projects. So even though the measures such as symmetry and complexity are something that are very ubiquitous within this field, they weren't necessarily able to describe the items that were generated or describe the kind of perception of these items. Okay, let's just a small brief talk about what's going to happen in the future. So one thing we want to do is be able to test using participants and kind of confirm these results, that we can create these kind of highly complex, highly symmetrical items using this process, and including other measures as well, not just symmetry and complexity, to help us kind of further show the versatility and understand exactly understand more about the process that we've generated. And as I mentioned at the beginning, we'll also be using this process to help look at identifying and formalizing the contributing aspects of 3D aesthetic judgment. So there's a lot of potential extensions we can also add. So if we're thinking about trying to create art with this process, which is exactly its intention, so there will be aspects, so extensions, so increasing the expression tree function set, implementing calculations for color of the items. And then, as we can see in the examples on the right hand side, we can use different geometric shapes to render the items, which changes kind of the visual properties of the rendered sculptures kind of entirely. And we can also add additional calculations to dynamically size the items as well. And we can see that again changes the visual kind of characteristics of the items that are generated. Okay, so thank you everyone for listening. I hope it was informative. And what we can see just in the background is just the range of the slide backgrounds that were generated or offered as part of this. But yes, if you have any questions, please feel free to ask.
Thanks for the presentation, Eddie. So let's move on to questions. Several people clapping, but I'm not seeing anybody raising hands. Okay.
Can raise my hand now.
Please go ahead.
Thank you, Eddie. A very interesting presentation. I was wondering, when you evaluate the 2D aspect of your generated artworks, do you only consider one view of the artifact?
Yes, so at the moment it's only the top-down view. But I think again that'll be something we'll potentially, as the extension is, having it from different angles and seeing how the characteristics change based on that.
Yeah, because at least from your last slide and some of the pictures that you shown from the top view, you can have really complex structures that in depth have a lot of items, but then from the top view, you only see a dot. So probably, well, try to make it so you pick several snapshots and apply the different metrics. I don't know, it could be one way to at least try to give a more smooth evaluation for your items, so you can get variability from the well, from your representation, and try to evaluate it in that form. And sorry, I know if you want to comment on that.
Oh no, I was just going to say, I think it's also going to be important when we're thinking about comparing the sculptures. I think you can, if someone views a sculpture from a particular angle, if we could then kind of recreate that in a 2D item and then apply these measures to it, we might get some kind of correlation or information, sort of interesting information from, yeah, reproducing that specific viewpoint rather than having to work in a 3D item. That might be, yeah, something quite important, I think. So yeah, be a good thing to add in, I think.
Okay. And I have also another question concerning evaluation. So you are, I'm quite sure you are measuring complexity with zipped compression. Can you elaborate more on that?
Yeah, so the Kolmogorov compression. So basically, we were encoding all of the points of each of the items in 3D space into a JSON format. So just the X, Y, and Z positions, and then we were comparing the uncompressed to the compressed file size from there. So basically, yeah. So then an idea to kind of the lower levels of compression that we achieve should be higher complexity on that.
Okay, it will. I think it will be also interesting to see how it would fare with other type of evaluations. Well, deep learning is in is on the hype for this, so try to capture patterns, different patterns or different aspects of your artworks from those from those inputs, and try to see how it goes in terms of in generation onwards. And also, if you, well, shameless publicity here, you can also check some work that myself and also Penousal Machado did on complexity metrics. I know, I think for some of those artworks that you expose, there could be some metrics there that you could also explore. But very, very interesting. I want to see more about this work. So
thank you.
Well,
sure. Well, yeah, I'm
Thank
sure we will do the next few years. Yeah.
Okay.
Thank you.
Any more questions? Don't be shy. Okay, you have a question on the chat, Eddie, from Bill. Can you read it?
Yeah. So brain is an example of symmetric and complex objects. So is this why you wanted to cover the whole of complexity and symmetry? So yes, so we can think about it in terms of that, and this kind of comes back to, as I was saying, about our perception of symmetry and complexity, where they can work in conjunction with each other rather than just being these kind of diametrically kind of opposing items within the artwork. So the main reason really was because we're going to be using this process to help kind of assess different kind of aspects of aesthetic judgment. What we really wanted to be able to show with this process is that we could create a wide range of items, some good, some bad, but to be able to cover the whole range of items is kind of an important aspect really for us to be able to generate them. And we chose complexity and symmetry mainly because they're very, very widely used, especially when we're talking about the kind of the Birkhoff formula and things like that as well, which symmetry and complexity in various kind of measurements have been used to try and help us identify that. So that's why we kind of went for symmetry and complexity with this. But yes, as we were just talking about, I think there's other measures that may be more appropriate, and that's something that we certainly will be kind of adding into this or using to kind of help describe our items.
And can I ask, which type of symmetry were you looking at?
So it's just reflectional symmetry across 3D planes. So basically the process works by placing or sampling kind of, I think it's 52 planes in 3D space, and then using optimization to be able to move these planes and determine whether there's kind of a decent level of symmetry across the plane, and using that to kind of calculate a particular or an average value for the entire kind of item.
So you didn't look at rotational symmetry, or it's just mirror symmetry you were looking at?
Yes, yeah, just is mirror symmetry at this time, yeah. But again, yeah, so rotational symmetry would be something that, again, we'd have to have a look into.
Yeah, in maths, there are many groups which have different types of symmetry, so that might also be something that you could consider in future.
Yes, yeah, thank you.
Okay, thank you.
Yeah, thank you, Bill. Very good suggestion. If I may add on to that, because I think we have time, because well, disclosure, I don't see the next speaker, so we have time for talking a little bit, so we can go on for a little bit more. I was going to follow up on Bill's comment on symmetry and also on complexity. I think symmetry is particularly appropriate for 3D structures because it can be seen as a proxy for balance. If you have a symmetric structure along the vertical axis, then this structure will probably be balanced in the sense that it won't fall to one side of the other, which would be a prerequisite for having a solid, robust 3D structure. I think you should also, because it's 3D, I think you should also probably look into balance. Balance even in 2D is typically deeply tied with the physical properties of the image. So, and when it comes to 3D, it's a direct, well, almost direct translated. We tend to perceive things as balanced when, unsurprisingly, they are balanced. And I was thinking you probably can do some sort of simulation to see if the structure resists to lateral forces and so on, and that could give you another degree. I had a question. When you are evaluating, if I got it right, when you are evaluating complexity, you are looking, let's put it like this, at the structure of the object and not necessarily at the rendering of that structure. Am I right, or did I miss something? It's not a criticism, it's just a question. Sorry.
Yes, so I think the complexity measure we used, so we kind of had two. So we had the compressibility one with the Kolmogorov compressibility measure, but the complexity measure we used was part of the rendering. So what we tried to do with that was try and get a ratio based on the number of visible vertices that were present within the sculpture. So this included things that, so trying to take into account items that were overlapping would have less kind of visible vertices. So anything that was kind of within a particular range, we discarded, and then basically, compared that to the kind of the maximum and got that ratio basically as a level of complexity there. So we had kind of two-ish measures.
So okay, got it. Well, as a follow-up to João's suggestion, I believe I can look into it later and send you the reference if I can find it. I believe there is some work on visualization of 3D structures that tries to find a view that better shows the structure. that was probably not very clear. And that could be a solution. Instead of looking at the top view or side view, trying to use an algorithm to show to find the most revealing view of the object, and then use that view to assess complexity. That could be interesting. Or maybe playing, well, so many ideas. We could go on forever, but maybe playing with the difference of complexity between or among different views could also be interesting, and so on.
I think you could do the same thing with the symmetry as well. As you could say, the way we detected it, we had the various planes being detected and then kind of optimized. You could then use that as a basis to place the views as well. So you could see which one has the best symmetry. Yeah, that'd be quite cool.
Yeah.